Dear students, in today's class we will discuss about standard first form of non-linear partial differential equation. Standard first form, that is a partial differential equation of the form f of pq is equal to 0, where meaning of this p is d over z upon d over x and meaning of q is d over z upon d over y. Means differential equations involving only p and q, means differential equations are not involving x, y, z. In standard first we have partial differential equation of the form f of pq, means differential equations contains only two terms p and q, where p is d over z upon d over x and q is d over z upon d over y. Suppose this is the equation number 1. The complete solution the complete integral equation 1 is given by z is equal to ax plus by plus c. Suppose this is the equation number 2. If we differentiate 2 partially with respect to x, we get here d over z upon d over x is equal to a. These two terms will be 0. When we differentiate partially with respect to x, we treat all other variable as a constant. Here we get p is equal to a. Next we differentiate equation 2 partially with respect to y. We get here d over z upon d over y is equal to b, that is q is equal to b. Now from 1 a and b are connected by the relation f of ab is equal to 0. This is called our equation number 3. We have to put value of p and q in equation 1. We get this. Now from 3, either we find out value of p in terms of a or value of a in terms of b from equation 3. Means from equation 3 either we find out b in terms of a or a in terms of b. And from equation 2, when we put this value of b, suppose we have this value, and from equation 2 we put value of b in equation 2, we get here z equal to ax plus phi a phi plus c, which is a required complete integral of equation 1. Okay, which is a complete integral solution of equation 1. Now next we find out general integral. Here suppose this is the equation number 4. Now here assuming here in equation form there are two arbitrary constants a and c. Okay. Now taking c is equal to some function of a, where psi is an arbitrary function, where psi is an arbitrary function. Now from equation 4, we get z is equal to ax plus phi ay plus psi a, and suppose this is the equation number 5. For general integral, next we differentiate equation 5 with respect to a. Suppose we can write it z is equal to, suppose we assuming this in terms of function, that is function f is equal to ax plus phi ay plus psi a minus z is equal to 0. Suppose this is the equation number 5, rewriting this as a equation number 5. Now next we differentiate 5 with respect to a, that is next we find out derivative f upon derivative, that is x plus phi dash plus psi dash a is equal to 0. This is our equation number 5. Here we can find the general solution by eliminating a from 5 and 6. The general solution, the general integral can be obtained by eliminating a from f equal to 0 and derivative f upon derivative equal to 0. That is from equation 5 and equation 6. Next we find out singular integral. Next we find out singular integral. Okay. Now from equation 4, we have z equal to ax plus, from this equation, this is the equation number 4, ax plus phi ay plus c. that is ax plus 5ay plus c. Okay, now in this complete integral of given equation, we have two arbitrary constants. We have two arbitrary constants a and c. Okay, suppose this is the equation number 7. Next we have to differentiate 7 partially with respect to a and with respect to b. What is the equation number 7? We have z is equal to ax plus 5ay plus 7 plus c. This is the equation number 7. Now we assume, suppose this is equal to f equal to z minus ax minus 5ay minus c is equal to 0. Okay, now differentiating f partially with respect to arbitrary constants a and c. First we differentiate this equation partially with respect to a. We get here 0 minus x minus 5 dash ay minus 0 is equal to 0. That is, suppose this is the equation number 7, that is minus x minus 5 dash a y is equal to 0, and this is the equation number 8. Now differentiating 7 partially with respect to second arbitrary constant c, that is 0 minus 0 minus 0 minus 1 is equal to 0, that is minus 1 equal to 0. In equation 9, minus 1 equal to 0 is not possible. Minus 1 equal to c is not possible means the given partial differential equation f of pq is equal to 0 have no singular solution. Okay, now we will try to understand standard first form non-linear partial differential equation with the help of some examples. Okay, now we take a problem. Suppose this is the given partial differential equation. d over z upon d over x whole square plus d over z upon d over y whole square is equal to 9. That is p square plus q square is equal to 9. Okay, Now we have to solve. This is a standard first non-linear type of partial differential equation. Now we solve it. Given equation, what is given? Our given partial differential equation is p square plus q square is equal to 9. This is the given partial differential equation. The complete integral, we know that the complete integral of equation 1 is given by z is equal to ax plus by plus c. Okay, here x and y are two independent variables, z is a dependent variable, and we have two constants a and c. Okay, now differentiating 2 partially with respect to x, we get here deriv z upon deriv x is equal to a, that is p is equal to a, and when we differentiate 2 partially with respect to y, we get here deriv z upon deriv y equal to b, that is q is equal to b. Now this a and b, these a and b are connected by the relation. Now from 1, when we put value of p and q from here in 1, we get here a square plus b square equal to 9. Here a and b are connected by this relation. Okay, now here we find out either value of b in terms of a or value of a in terms of b. Suppose we are finding out value of b in terms of a. Here value of b is, that is b equal to plus minus under root 9 minus a square. Now we put this value of b in equation 2. From 2 we get a z equal to ax plus minus under root 9 minus a square y plus c, which is a complete integral of given equation. Now we will try to find out its general integral. Suppose this is the equation number 3. Now we try to find out general integral. Okay, how we can find out general integral? For general integral, first we assume we taking c equal to some function of arbitrary constant a. This is equal to some function of arbitrary constant a, where psi equal to psi a, where psi is an arbitrary function, is an arbitrary function. Okay, now from equation 3, what we get from equation 3? We get z equal to ax plus minus under root 9 minus a square y plus psi a, and this is called suppose equation number 4. Next we differentiating 4 partially with respect to a. For singular solution, first we differentiate this equation partially with respect to a. What we get here? 0. Here when we differentiate with respect to x, then with respect to a, remaining term will be constants, remaining variable or terms will be constant. That is, here we get x plus minus, here we have 1 by 2 9 minus a square to the power 1 by 2 minus 1 into minus 2a y plus side as a. This is called equation number 5. Okay. Next we have to eliminate. Here general integral can be obtained. General integral can be obtained by eliminating a from equation 4 and 5. Okay. Next we find out singular. Next we discuss about singular integral. We have from equation 3 we have z is equal to ax plus minus under root 9 minus a square y plus c. This is we have from equation 3. Okay. Now we can assume this in the form of function. Here f equal to z minus ax minus plus 9 minus a square y plus c. Next we find out derivative f upon derivative equal to 0. That is 0 minus x. We differentiate this partially with respect to x minus plus 1 by 2, and here we have 9 minus a square to the power minus 1 by 2 into minus 2a here into y plus 0 equal to 0. And when we differentiate this partially with respect to b, we get derivative f upon derivative b, derivative b upon derivative c. Here second constant is c. That is, we get here 0 minus plus 0 is equal to plus 1 is equal to 0. Here 1 equal to 0. From this relation we have 1 equal to 0. Okay. we can say this is our equation number 6 and this is equation number 7. Means here we get 1 equal to 0, which is not possible. Means this non-linear partial differential equation p square plus q square equal to 9 have no singular solution. That is partial differential equation p square plus q square equal to 9 have no singular solution, have no singular integral. Okay, now we take some more examples for better understanding of standard first non-linear partial differential equation. Okay, next we take another example. Find the complete integral of the partial differential equation x square p square plus y square q square is equal to z square. Okay, here initially it is not in standard form, but we can convert this differential equation in standard form by taking some substitution. Okay, what we have here we have differential equation. We can write this differential equation in this form: x upon z. Here meaning of p is diver z upon diver x. X upon z diver z upon diver x whole square plus y upon z diver z upon diver y whole square equal to 1. Here p is diver z upon diver x, q is diver z upon diver y, and now here transferring this term in denominator. Here we can write it x upon z diver z upon diver x whole square plus y upon z diver z upon diver y whole square equal to 1. Equivalently we can write in this form. Okay, now we have three substitutions. One, diver x upon x equal to diver capital X, diver y upon y equal to diver capital Y, and diver z upon z is equal to diver capital Z. Okay, now when we integrate this, what we get here? Log x equal to capital X, log y equal to capital Y, and log z equal to capital. Integration of 1 upon x is log x, integration of 1 upon y is log y, and integration of 1 upon z is log z. Now we can write equation 1. We can write it diver z upon z is diver capital Z, and diver x upon x is diver capital X. We can write it diver z upon diver capital X whole square plus diver z upon diver z is diver capital Z, and diver y upon y is diver capital Y whole square equal to 1. Okay, now assuming capital P is equal to diver capital Z upon diver x, and capital Q is equal to diver capital Z upon diver y. That is, we can write this equation in the form capital P square plus capital Q square equal to 1. Okay, now this is in standard first form. Now we can assume complete integral of this differential equation as capital Z equal to A capital X plus B capital Y plus C, which is a trial solution of given differential equation, because in this differential equation we have dependent variable as a capital Z and two independent variables capital X and capital Y. According to these dependent and independent variables, we assume complete integral as a Z equal to AX plus BY plus C. This is the complete integral is given by this equation, Z equal to AX, A capital X plus B capital Y plus C. Suppose this is the relation number 3. Next we differentiate diver capital Z with respect to diver capital X. We get this A means we get here P equal to A, and when we differentiate this capital Z with respect to capital Y, we get here B, that is Q equal to B. Now from this equation, this relation, we replace diver Z upon diver X by A and diver Z upon diver Y by B. Now from this relation, P and Q are connected, A and B are connected by the relation A square plus B square equal to 1. Okay, so put the values of P and Q, that is A and B, into, we get this relation. Here we will find out value of B in terms of A, that is 1 minus A square to the power 1 by 2, or sometimes we can find out value of A in terms of B. But suppose we are finding out the value of B in terms of A, that is B equal to plus minus under root 1 minus A square. What we get here from equation 3, from this equation, now we put this value of B in 3. From 3 we get Z equal to A capital X plus 1 minus 2 A square to the power 1 by 2 capital Y plus C. Which is now our original variables all are small x, small y and small z, and we can replace, we can replace this capital XY log x, capital YY log y and capital Z by log z. That is, this is capital Z, here we have log z equal to A log x plus 1 minus A square to the power 1 by 2 log y, and here we can take constant in any form. Suppose we are choosing this C equal to log C, then what we get, and we can also simplify it. Suppose if we choose A equal to cos alpha and this C equal to log C, for just for simplification of this, constant can be, we can take constant in any form. Okay, what we get here we get Z equal to cos alpha log x plus 1 minus cos square alpha, that is sin square alpha to the power 1 by 2, that is sin alpha log y plus log c, and we can simplify it we can write it z equal to log x to the power cos alpha plus log y to the power sin alpha plus log c. Okay, that is z equal to log m plus log n plus log r, means log m into n into r. Here this is log z. It is very much clear. This is log z, log z, log z and log z. Okay, so means log z equal to log c into x to the power cos alpha y to the power sin alpha. We can simplify it, that is z equal to c into x to the power cos alpha into y to the power sin alpha. Here this is the final solution. There is no need to proceed further, and this is, we can say, this is the complete integral. You can stop here and you can also simplify it. You can also choose this a equal to cos alpha. Here a and c are arbitrary constant. We can choose any value for that. A equal to cos alpha, c equal to log c. Here we choose c equal to log c, and when we simplify it, we get this relation. We can say this is the complete integral of given partial differential equation, and also we can stop here also. Okay, if we want to find out general integral, we can also find out general integral. Now we take another page for general integral. Suppose this is our equation number 4. Suppose this is our equation number 4. Okay. Now we try to find out this is our equation number 4. Here we have z equal to c into x to the power cos alpha into y to the power sin alpha. This is our equation number 4. For general integral, taking c equal to psi in terms of the function of this alpha, or if we have a, then function of a, c equal to psi alpha, where alpha is an arbitrary function, where psi alpha is an arbitrary function. What we get from equation 4? From equation 4, we have z equal to psi alpha x to the power cos alpha into y to the power sin alpha. Okay, this is called equation number 5. For general integral, first we differentiate 5 with respect to alpha. Okay, when we differentiate with respect to alpha, we treat z as a constant. Here differentiation of z with respect to, now first we write here differentiating 5 partially with respect to alpha. What we get here? That is, differentiation of this is 0 is equal to. Now we apply product of two function formula. This is first function and this is second function. Differentiation of first. Differentiation of psi alpha is psi dash alpha. Okay. Differentiation of function we denote, suppose, by dashes. The first differentiation of first, second as it is x to the power cos alpha into y to the power sin alpha plus psi alpha as it is, and differentiation of this. First we differentiate x to the power cos alpha, that is x to the power cos alpha, and differentiation of this cos alpha is minus sin alpha and log x to the base e, and second term as it is means y to the power sin alpha plus differentiation of first means y to the power sin alpha. Differentiation of this sin alpha is cos alpha, and here log y to the base e, and second term as it is x to the power cos alpha. Okay. Here we know that differentiation of, what is the formula of how we can differentiate x to the power alpha? X to the power alpha, what is the formula of dy dx of x to the power a? It is with respect to alpha. So x to the power alpha, differentiation of this x to the power alpha, differentiation of x to the power a to the power x is dy dx of is a to the power x log a to the base e. Okay. Now suppose this is the equation number 6. This is the equation number 6. Now eliminating, now general solution, can be obtained by, this is the equation number 6, by eliminating alpha from 5 and 6. Okay. Next we discuss about singular integral. Here we have this equation z equal to c x to the power cos alpha into y to the power sin alpha. Here we have 2 from equation 4 here we have two arbitrary constant alpha and c. Okay, now we differentiate four partially with respect to alpha and c. Now what we get here when we differentiate 4 partially with respect to alpha, we get here diver z upon diver alpha is equal to that is 0 minus c 0 is equal to minus c into x to the power differentiation of x to the power cos alpha, that is x to the power cos alpha minus sin alpha log x to the base e plus and second term as it is, that is y to the power, we apply product of two function formula plus differentiation of this term, that is c into x to the power cos alpha, that is cos alpha y to the power sin alpha, and differentiation of sin alpha is cos alpha and log y to the base e, log y to the base e. Okay, and next we differentiate 4 parts. This is equation number 5. Next we differentiate 4 partially with respect to c. What we get here when we differentiate this with respect to c, we get here z equal to, here we have 0, here we have 1 into x to the power cos alpha and y to the power sin alpha, and this is the equation number 6. Now we have to eliminate alpha. Now we have to eliminate alpha from these three equations. We can simply put the value of x to the power cos alpha, y to the power sin alpha in 4. We get here z equal to 0, which is a required singular solution. I think all you have understand this standard first non-linear partial differential equation easily. If you have any kind of queries regarding non-linear standard first type partial differential equation, then you can mail me. This is my email ID. Okay, thank you very much. Good day and Bharat Mata ki Jai.